So after this longish introduction, let's just jump to the main topic of this lecture, which will be about mapping the service model and the autonomous system level business relationships into actual AS level passes. Let's just again recall a couple of definitions. So now we are going to just discuss interdomain routing. So from this point, we are not going to describe intradomain routings like OSPF. We are not going to describe IBGP, which is the version of BGP that runs inside an autonomous system to distribute external routes within the autonomous system. We are going to just delve with a very simple model where the internet will be modeled at the autonomous system level, and we are going to just try to see this autonomous. We are going to just consider this simple autonomous system level view of the internet and try to describe these AS level passes that arise on top of this very high level view of the internet. We are going to just see that even considering the complexities that emerge from the use of IBGP and the EBGP and IGPs and these questions or complexities of the interaction between routing protocol instances. Just this AS level view is already complex enough to confuse most of us. So that's why we are just stick to this simple view of the internet, where the internet will be made up by EBGP itself. And in this context, we are going to talk about routing policies, which will be the mechanisms to represent the particular autonomous systems business strategies in the way forwarding passes are provisioned by an AS. As we've seen, the decision whether to two ASes to connect their networks with a physical link and the mechanisms that drives these decisions is typically a business oriented one. So it is the business strategies for profit oriented enterprises like internet service providers that dictates the way the internet topology actually emerges from these autonomic decisions of different autonomous systems. The question that we are asking here is how these business strategies will be mapped to actual forwarding passes, or how these forwarding passes will represent the business strategies of the ASes that make up the internet. So we, of course, in order to map the business strategies to actual forwarding passes, we'll need sophisticated routing protocols, and this routing protocol must be a routing policy routing protocol, which will be able to just realize this mapping, and this will be BGP. Now, how BGP actually just transformed these high level and highly virtual business relationships into actual forwarding passes, this will be revealed in the subsequent lectures. Here we are just going to describe a very simple model that for us we will use as a model to at least for us build a mental model of this process. Of course, again, we're going to just see that the configuration of BGP in individual BGP instances will be much more difficult than the model the simplified model that we just described here. So the first question that we ask is how to encode the AS level business interests into actual forwarding passes. Now, what are these actual business relationships that we discussed or we talk about so much? Recall that these are in our single service model. These are described by the transit and the peer relationships that may exist between two ASes. So two ASes typically establish one of these types of business relationships between one another. In the transit, the provider autonomous system sells global internet access to a customer autonomous system for a monthly fee. Recall that this transit relationship pretty much resembles the way we actually connect our home network to an ISP's network. It's just the two participants in this case are autonomous systems. The other type of business relationship that we do not really see at the customer internet service providers business is the peer relationship, which is a special type of business contract that may exist between two autonomous systems, where they decide to exchange traffic between each other and between any of their customers for free. And recall that the idea is basically to save on transit fees. We are going to just focus on these two specific types of business contracts in the rest of this lecture, and actually in the rest of this lecture series as well. But we are try to stress here, and later on we are going to just recall this a couple of times, that reality is much richer than that. But even the routes that arise on top of the transit and the peer relationships are already complex enough for us to understand, and this will model a sufficiently large portion of the reality for us to give a very good understanding of what's going on in the AS level routing of the internet. So the second question that we ask in the second part of the lecture is that how do routes induced by the transit and the peer relationships look like? Recall again, whenever we have a complete view of an internet, of a smaller portion of the internet with hosts, switches, and routers and different autonomous systems, instead of this very complex view, we're going to just use a simplified schematic diagram where autonomous systems will be represented with a single graph node, and there will be a link between two such graph nodes if there is a relationship. In this particular case, when there is an arrow, then there is a transit relationship between these two ASes. The other type of relationship might be the peer relationship, where the lack of an arrow actually indicates that there is no cash flow in this particular setup. So this simple setup in the peer relationship will just represent that very simple business relationship between AS1 and AS2, that they want to exchange their and their customers' traffic directly with each other through this peering for free, instead of going through a provider which will charge transit fee for such traffic exchange. If we want to just remove the transit provider from the loop and save on transit fees, then these two ASes can form a direct peering relationship with each other, and this particular peer relationship will be represented by this arrow in our schematic diagram. In the rest of this talk, we are just describing the internet using these schematic diagrams, and the passes. The graph will consist of ASes. The links might be peer links or transit links, and the passes between different ASes will be successions of ASes. But please always recall that underlying this schematic diagram there are ASes, and the ASes themselves can hide fairly complex internal topologies, but we are going to just forget about the internal structure of ASes in order to be able to concentrate on the AS level, high level architecture of the internet. In order to understand the types of routes that may exist in the internet, we need to introduce two simple terms or simple definitions. These are the definitions of the feasible and the prohibited passes. So the forwarding passes set up by ASes reflect the business and policy interests of the different service providers or the different autonomous systems that make up the internet. In this setup, a feasible pass is a pass between two autonomous systems that aligns with the business interests of all the autonomous systems that participate in this pass. So not just with the two endpoints, but all the intermediate ASes too agree to actually forward pass on a feasible pass. So for instance, then going to see that a transit pass from a customer to basically any of the other ASes on the internet is a feasible pass, because there is an economic incentive for the provider to route traffic along that path. The forbidden path, in contrast, is a path whereby forwarding, so there will be at least one intermediary AS along the path that will not be interested in forwarding traffic along that path, so this will not align or will go against the economic incentives of some of the ASes, at least one AS along the path. We're going to see examples in a minute. Now, suppose that let's just forget a little bit about peer paths and assume that the internet consists of transit relationships only. If we just consider this very simplified view of this internet architecture, which are the types of paths that may arise in this model? Let's see feasible paths. Consider, for instance, a customer that buys internet transit from two provider ASes. Recall that this setup is called multi-homing, and suppose that there is a remote AS somewhere in the internet, and we are asking which are the types of paths that may arise in this simple setup. In order to understand this, in order to decide, for instance, whether, for instance, this particular path is a feasible path or a forbidden path, we need to just understand the business interests of each of the ASes along this path and ask whether the business interests in this particular setup will align, of the ASes will align with forwarding paths along that path. Now, for instance, here we see that the only AS that may block the forwarding of traffic along these paths is provider 1, or if we consider this path, then this is provider 2. Now, what we see here is that instead of blocking this, both AS1 and AS2 are actually very much interested in forwarding traffic along these paths. Why? Because any packet that traverses these transit links will bring profit through the transit fees to the transit providers. So it's not just that it's an economic incentive to leave or let traffic to flow along these paths by the provider ASes. It is actually within their economic interest to attract as much traffic to their provider link as possible, because this is a profitable service that they provide to the customer AS. The more traffic, for instance, that AS1 manages to attract to its transit link, the more transit fee it will be able to charge on the customer AS, and the higher the profit. So actually, any path that goes from a customer through a transit provider to a remote AS, or the other way around, will induce transit fees on this link, and this is within the economic interest of this provider to actually allow traffic to flow along that path. Same stuff with AS2. What is prohibited, or what is a forbidden path, is basically just this simple setup. In this case, the customer AS will not be interested in forwarding passes, forwarding traffic between two of its customers. Why it is the case? There are lots of reasons why the customer AS will block the flow of traffic through this path indicated by the red arrow in this little figure. One is for every bit of traffic that it transits along this red path, it will be charged 2 times, both for AS1 and AS2 on the transit link. So it will just recall that the transit business relationship will be about customer AS paying AS2 to provide its own traffic access to the internet, and this contract does not cover forwarding traffic between two of its autonomous two of its providers. So in this setup, this red path will be blocked. Most of the time, even the providers are not interested in these types of forbidden paths, because usually the customer AS's network resources are not adequate to route the provider AS is usually much higher volume of traffic, and therefore this is exactly the case. While most of the time the ASes will establish a different a direct peer relationship with themselves, and instead of using the customer, they will use this direct peer link to exchange traffic. So in this particular setup, when we consider only transit links, basically all passes starting from a customer AS or terminating in a customer AS will be allowed, or will be a feasible pass, but any pass that goes from one or two providers of a customer AS will be a forbidden pass. The situation with the peer relationship is a little bit more different, more difficult. Recall that the idea in the peer relationship is that the AS6 and AS7 will want to save on transit fees. Now any pass that goes from any of the customers to AS6 and any of the customers to AS7, AS6 is actually contracted by AS4 to route all of its traffic to the internet, and this is the same stuff for AS3. So these AS6 and AS7 will be actually contracted to exchange these types of traffic somehow. Now, if they didn't have this peer link, or they had this peer link but they wouldn't allow traffic to flow along that path, then they would need to use the transit providers to exchange such traffic. Recall that they are contracted, so they are actually it is obligatory for AS6 and AS7 to route and forward these types of traffic. So there is an economic incentive to allow packets to flow along that peer relationship. Instead, this is the very reason why they established the peer relationship between themselves, in order to be able to save on the transit fees that would be otherwise incurred by their transit providers for exchanging this link. So in this if we just try to remember this simple definition of what the peer relationship is, and recall this definition is to exchange, to actually save on the transit fees that would otherwise be incurred by the transit providers, then this will actually be a very simple guideline for us to decide on which are the feasible passes on peer links. Basically, any pass that goes from the peering ASes themselves, or any customer of a peer and any other customer of the other peer will be allowed to flow along that path, flow along the peer relationship. What is forbidden is basically everything else. Okay, so for instance, in this particular setup, AS6 will be not interested to route between one of its providers and its peer. This is the type of forbidden passes which usually causes the most mistakes when people have to decide between feasible passes and forbidden passes. So this is the type of passes that most people actually get wrong when solving little tasks. And the very reason for AS6 to block these passes is that because its economic incentives goes pretty much against routing or forwarding traffic along that path. Just it does not have anything to do with AS9's and AS7's packet. It does not really. So it is basically not interested in how these two guys will exchange traffic with each other. If it allowed traffic to flow through its network along this red path, this would actually mean that it would need to pay transit fee to AS9 after every single bit that it allows to flow along this path, even though it is not contracted by neither AS9 neither AS7 to route traffic along that path. So it will just basically block these types of passes. The same goes for the succession of two or three or more peer links. These are also forbidden passes. If AS5 will want to exchange traffic with AS7 through AS6, then AS6 will basically just say, okay, if you want to exchange traffic along that path, just pay me transit fee. Okay, we are just step it out ourselves and rather go to a transit relationship, and then I will charge monthly fee for you to exchange traffic through my autonomous systems, but otherwise it will not be interested in elliptic traffic to flow along any path that traverses two or more peer links. And that's the third type of prohibited paths when we are talking about peer relationships is these types of packets. So neither AS6, neither AS7 will be interested to exchange traffic between two of their providers. The providers will need to take care of exchanging their traffic themselves, because just recall, both AS6 and AS7 would be charged by their respective providers by every single bit of traffic that is forwarded along the thread path, and this is of course are against their economic incentives. If we just think a little bit about the types of paths that arise in this simple model, we're going to arrive to something which we are going to just call the value free routing property. In fact, if we visualize the internet architecture, the AS level architecture, using the transit hierarchy that we described at the end of the previous lecture, and we are just drawing the individual paths within this AS level architecture, we're going to see that forbidden paths always have these types of small valleys in them. So any valley is essentially a violation of one of the routing policies or the economic interests of some ASes, usually the ASes that are at the bottom of the valley, and that's why the paths confirming to the transit and peer relationships usually do not contain valleys, and this is where the name comes from. So essentially, this is high-level idea about the types of paths that usually are established in this AS level infrastructure, is that they are value free. Let's try to make this idea, a little bit vague idea of what we mean by being value free, a little bit more explicit. Let's just define value free paths explicitly. We are going to say that the path is value free if it contains first 0 or more links that go from a customer to a provider, then exactly 0 or 1 peer link, and from that point 0 or more links that go from a provider to a customer. So any feasible path in the internet, when it is drawn in the transit hierarchy, will have this property that the packets will first travel upwards in the transit hierarchy from a customer to a provider. Then it will make at most one horizontal step from one peer to the other, traversing at most one peer link. And from that point, packets will travel downwards from providers to actual customers. What's very important is that these through phases, customer to provider, peer, and provider to customer, any of these phases may be missing. Okay, so this is also a value free path. This is also a value free path. The idea here is that it first goes upwards, then it takes at most one horizontal step, and then the value free path go downwards. Let's make this idea even more explicit. Okay, so how to actually check the value-free property. We can use the previous definition, and it will make sense most of the time, but maybe this is still not exact enough or explicit enough for us to be able to solve specific problems. So we're going to build a formal model and a formal calculus to actually decide whether a particular path is value-free or not. And for this, we are going to just convert our schematic diagram into a labeled directed graph model. So what we are going to do is that we are going to represent the AS level topology with a directed graph. The nodes in the graph will be the ASes, and the arcs or the links will be as follows. The transit link in the customer to provider direction, so upwards, will be represented by a directed link which will be marked by a label P. The same transit link downwards, so from a provider to a customer, will be marked by the label C. So this is about the transit relationships. In contrast, the P relationship in both directions will be represented by a directed link labeled with this label R. Okay, why don't we use P to label peer links? Because P is actually taken by the provider links, so we use the other another letter from the word peer, and this will be R. Okay, now using this very simple conversion rule, we take the schematic diagram and rewrite it into a very nicely structured labeled directed graph representation, where again the nodes are the same, so they are autonomous systems, but transit links will be substituted by P and C, the directed links with labels P and C, and peer links will be substituted by two links marked by the letter R. Now, wherever we have this graph representation, this representation will be very useful for us to be able to decide on value-free paths. In order to understand how, let's just look at a concrete example. So we ask first whether the path from AS6 to AS8 that is marked by this blue arrow is feasible or a forbidden path. We are going to use the previous and directed graph representation to decide this question. So first, again, we take this is our schematic diagram. We just describe this. We just convert this into the directed graph representation with these label arcs, and then draw the previous path in this representation, and take the labels alongside the path in the order given by the direction of the path. So we have a path for the path goes from AS6 to AS3, AS1, then AS4, AS5, and AS8. So if we just read out the labels along the directed links that make up this path, then we get P and P, and then the path goes downward, so we get a C, and then the path takes a horizontal step, so the label is R, and then the last label is C because the path takes a downward step in this directed graph representation. So if we just enumerate all the labels along the directed path and write them one after the other, we get the succession of the labels P, P, C, R, C. We're going to use this little string P, P, C, R, C to decide whether a path is a forbidden path or a feasible path, and the theorem that we use to decide on this is the following. Path is forbidden if and only if it contains a two-hop path marked by CP, CR, RP or RR. Okay, so this is the 4 cases that we need to remember whenever a pass contains a succession of 2 links marked by C and P, or C and R, or R and P, or R and R, then this is a forbidden pass. Every other pass is a feasible pass. So if we just go back to the previous example, we're going to just see that P at P is allowed, P and C is allowed, but C and R is a forbidden pass. Okay, so this is exactly the second type of forbidden pass. And therefore, the blue pass and the succession of P, P, C, R, C is a forbidden pass in this simple example. Okay, if you know what a regular expression is, then you can also use the regular expression form to decide whether a pass is feasible or not. A regular expression is essentially a context-free grammar to decide whether some input corresponds to a particular pattern, and in this case, asterisk means that 0 or 1 or 0 or any number of occurrences of the previous label, and the question mark means exactly 0 or 1 occurrence of the previous label. So this regular expression is essentially an explicit and formal representation of the rule that we described here, that any value-free pass first starts with a portion that goes from customers to providers. Recall these are the P labels. Then it may contain, so that's how we get P asterisk, and then we get at most 1 link, at most 1 peer link, so this is R question mark, and then goes from providers to customers. So again, it may contain any number of C labels, and if so this is the regular expression that we get in this simple theorem. Whenever a pass, so the succession of the labels and the string obtained by taking the succession of the labels along the path in the directed graph representation, whenever it actually matches this regular expression, then this is a feasible pass. Otherwise, it is a forbidden pass. So this is the way we decide on the feasibility of this blue link. Again, since this does not match the regular expression, the previous example gives us a forbidden pass, and the reason for that is that it contains a forbidden subpass. If we just go back to the definition, then this is exactly these types of subpass, which we marked by a red arrow. And when we describe the types of feasible and forbidden passes that we may get on a peer relationship, and the reason for why this is an actually forbidden pass, because AS6 is not interested in forwarding traffic between one of its providers and one of its peers, because it would be charged by transit fee and by AS9 for these passes. So it will just actually block these passes, and will let AS9 and AS7 handle the exchange of such traffic themselves. And here we can see these types of exactly this type of subpass that is forbidden. And since CR is forbidden, we get that the blue pass is actually forbidden. Let's see this other example. In this example, we have the blue. We have to decide whether this pass between AS6 and AS8 is a feasible pass or forbidden pass, and how we actually do that. First link is a customer to provider link. So this is we get label C. Then we get the customer to provider pass. So this is again P. Then we go from provider to a customer. Label is C, and the last label is provider to customer. So it's again C. Does it match the regular expression? Of course it does. It contains any number of P links. Then exactly 0 peer links, and then any number of customer links. So in this particular case, we get that this pass matches the regular expression, so this is feasible. And the last example that we use, AS6 to AS8, provider link, then succession of 2 peer links, and the customer link. This has this nice property that there is no value in this pass, but we see that there is a forbidden pass forbidden subpass in our passes, or in other way, the regular expression will not allow multiple peer links to come or to appear in a feasible pass, and this brings us to the observation that this particular example, the blue arrow, the pass marked by this blue arrow, is an actually forbidden pass. And finally, let's just try to refine this model that we get with very-free routing a little bit more. Very-free routing basically gives us the idea of which are the passes that are made available to a particular autonomous system by the rest of the internet. So this is basically just a level 0 rule that filters all the passes, but in on itself it will not give us any idea how will actually a router will choose between the types of passes, or between the passes that are available to it and that are communicated to it by the respective neighbors. So instead of just taking this high-level idea, let's just look into a very particular example. In this particular example, we have an AS3 that has 3 passes to AS6 in this simple schematic diagram. I would like to ask everyone to convince themselves that all the passes marked by the blue arrow, the light blue arrow, and the orange arrow are actually feasible passes and very free passes by the previous rules that we described in the previous slides. So as long as you don't understand why these passes are actually very free, as long as you don't understand why these passes all align with the economic incentives of all the ASes that they traverse, then please stop a little bit here and go back to the previous slides and try to understand the gain, because from that point we'll need the definition of the very free property to be able to further refine our discussion of routing policies. So again, AS3 has 3 very free passes here. The dark blue pass goes directly to AS6 along a customer link. The light blue pass goes through a peer, and from that point it goes to AS6, and the orange pass go all the way through AS2, and from that point it takes downward steps to AS6. Question is how AS3 chooses between each of these very free passes. Since each pass in this setup is a very free pass, all of them will align. All of them are traversable by AS3. AS3 will be free to choose between any of these passes in this little setup. How does it actually choose between them? If it chooses the transit pass, then recall AS2 will charge AS3 for any traffic that it routes along this pass. So as a simple rule, we just say that an AS3 will refrain from using that pass whenever it can, so it will only just use AS2 if there is absolutely no other way to get traffic to the destination. But in this particular case, it has other choices. It may use the peer link through AS4, and exactly this is why the peer link is there to exchange local traffic between AS3 and AS4 or the customer traffic. But in this case, it might be the case that AS3 might just overwhelm this peer link with traffic. So whenever there is other choice, AS3 will actually refrain from using that path. And again, in this particular setup, there is a very simple path through AS6. In fact, if AS3 routes traffic along with that path, it will actually be able to charge transit fee because AS6 is its customer. So it will be very, very interested in using the dark blue link to reach AS6. This is the path preference rules described a little bit in more detail, but the end result is a path selection rule which we will describe, or which we will call the prefer customer rule, which says that the typical ISP will prefer passes via a customer if such a pass is available. So the preference order is the following. Whenever an AS has multiple passes to a remote destination, it will first try to choose a path which starts with a provider to customer link. Okay, recall that the label for these types of links is C. So wherever the path is available that starts with the label 3 in the directed graph representation, an AS will try to choose that. If no such path is available, then a path that starts with a link labeled with R will be chosen. And if neither a provider to customer, neither a peer-peer link, a passive with peer-peer link is available, then the AS will use the transit path, because recall this will incur transit prices. So if we just describe this simple setup in the previous AS graph model, then we get the simple observation that if we take the first link of the path, so recall that the upper path is P, C, C, the light blue path is R, C, and the bottom path is just simply C. If we just take the first link of the passes, then we will be able to use this very simple distinction that the customer path will be preferred over a peer path, which will be in turn further preferred over a provider path. And this is the big idea in prefer customer rule. Whenever there is a customer path, we use that. If no customer path is available, then we use the peer link. If a peer link is available, and if neither a customer path nor a peer path is available, then only that case we use the provider link, because the provider will actually charge transit fee for these types of traffic. This is the prefer customer rule. It's described formally in this slide. This is basically just an order relationship that is defined on our simple labels P, C, and R. C is preferred over R, and it is preferred over P. Sometimes there is strong incentive to not use the prefer customer rule. In this particular simple setup, imagine that AS1 has a very long and maybe very poor quality customer path to AS4, and it also has a high quality transit path through AS2 transit provider to the same AS. In this case, AS1, by the definition of the prefer customer rule, would use this long customer path, but by its lower quality, it may very well happen that it will refrain from using this particular customer path and will rather go against the prefer customer rule and choose the transit provider to route traffic along that path. So this is just for you to show, to demonstrate that the prefer customer rule is not something which is an exact formal rule that is adhered to by all the ASes that make up the internet. In particular examples, in particular special cases, ISP policies might differ from what the preferred customer rule would provide, and because what path actually chosen from the set of very free passes that are available to a particular AS, it is the sovereign decision of an operator to decide. The preferred customer rule and the very free routing rule are just for us giving a mental model that describes a very good and an economically very nicely validated model of what's going on out there in the internet, but the real rules can be infinitely more complex than that. Now, what if a particular AS, in this case AS1, has multiple equally preferred passes to a remote AS? So for instance, in this setup, AS1 has two passes to AS3. One is a 2-hop customer pass, and the other is a longish customer pass, and then goes through, say, 4 or 5 customer links as well. Recall that both passes are very free. Both passes are preferred the same by the preferred customer rules because both are actual customer passes. If this is the case, so if two passes are also very free and the two passes are also put the same preference by the preferred customer rule, then usually the third tie-breaking rule that ASes use to choose forwarding passes is the shortest AS pass policy. So if there are multiple equally preferred very free passes available to a remote prefix, then the shortest AS pass policy says that pick the shorter one. So in this case, this short 2-hop pass will be preferred over the long equally preferred pass. And the order of evaluation in policy routing and internet policy routing is the following. Take all the very free passes available to a router, choose the one that is most preferred by the preferred customer rule, and if you still left with multiple equally preferred passes by the preferred customer rule, then pick the shorter one. These three simple policies, very free routing, the preferred customer rule, and the shortest AS pass length policy will be our guideline to understand the types of passes and the architectural or the structural properties of the interdomain passes that arise in the internet. And the rest of the lecture will be about how to actually encode very free routing, preferred customer, and shortest AS pass to actual BGP routers, because we want to just stress again and again that this model, very free, preferred customer, and shortest AS pass, is on the one hand just a mental model for us to actually understand what's going on out there in the internet, but the internet uses different mechanisms to decide on the passes. And second, even if we accept that the BGP configurations in the internet are actually set up in a way so that what the routing system and the AS level passes that emerge on top of these BGP configurations will adhere to these policies. The transit and the transit and the peer types of business relationships only just cover maybe something like the 60 or the 70% of the types of business contracts that may exist between two autonomous systems, and that's why the reality and the internet interdomain routing system is much richer than the model that we described here. But we're going to see in the next lectures that even configuring this very simple setup is already a complex enough task for us to make us busy during the rest of this lecture series.